All right, everyone. Thank you for coming to my MTL MTL versus free deathmatch. My name is John DeGoes, and I am quite surprised to see Daniel Spiewak here sitting in the front row. He's a well-known John A. DeGoes heckler. And I thought I would be free this year because the talks have no speaker names, but one of you ratted on me and told me. So he is here to heckle me, and he promises to heckle me within my first slide, so watch out for that. So this is what we're going to cover today. We're going to talk about composable effects, and then I'm going to present our two contenders. In one corner we have MTL, and in the other corner we have free. And they're going to duke it out, and at the end I get to pick a winner. And you get to disagree with that as much as you want. But remember, we only have like 30 minutes, so you may have to disagree in the hallway. So let's get started. What are MTL and free all about? Well, MTL stands for Monad Transformers Library, which is the reigning king of monad transformers, probably among all programming languages, and a lot of other programming languages, like PureScript and Scala, have copied MTL's design into their language. So actually, all the code snippets I'm going to be using are PureScript because that's all I write. I actually don't write Haskell, or haven't for some time, because of all the time I spend writing PureScript. But PureScript's library copies MTL. And then free is another abstraction I'll talk about in a second. And both of them are designed to solve the problem of composable effects. So yes, go ahead. Question there in the front row. What's your name, young man?
My name is Your Doom. Isn't this entirely a false dichotomy? MTL versus free? I mean, like, MTL is
versus M. I know.
Well, no. I mean, MTL is about managing monad transformer stacks, which, in a sense, can be viewed as managing effects. But free is sort of applicable to very different questions, where you have like a sort of a confined algebra, a closed algebra that represents a certain thing. You're not using it to represent optionality, or you're not using free as a primitive at the end of the world to represent your composable concurrency or anything like that. So why is it MTL versus free? Why aren't you telling us how to use MTL with free?
Good question, and actually in day-to-day programming I do use MTL with free.
See?
Yeah, so I'm a hypocrite, yes. But nonetheless, I do think that MTL and free can both be used to solve the effectful problems in the purely functional world, and that they have different approaches to solving that problem, and that they have different trade-offs. So while it's not strictly MTL versus free, MTL versus free makes for a much more inflammatory talk that's going to attract people like you.
But I think in alternatives, Oleg has a series of workshops to go pretty far down the free track without resorting to MTL to try to get some of the same benefits, right?
Yeah, that's right. Extensible effects, which is just a beautiful sort of modern day incarnation of free.
Continuation monad.
Yes. So contestant number one, MTL. Monad transformers have existed all the way back since 1989. That was the first sort of reference I could find to a monad transformer. And actually, just 6 years later, there was a ton of early papers after Moji's paper on that, or note or lecture notes, whatever it was. There was a ton of papers, and they advanced really quickly. So they went from having relatively nothing to having what I would say modern day MTL in the span of 6 years. And since then, not much has changed. The libraries have gotten better. Type inference has gotten better. All sorts of things have gotten better. We've figured out how to use these things, how to make them work really, really well within the confines of effectful programming. But still, that's been around for, 21 years? That's a long time. So it should not be surprising to any of us that MTL is the go-to for composable, modular, effectful programming in purely functional programming languages. Free, on the other hand, the first reference I could find to free was in a 2007 paper. Maybe it occurred before that. But I included a little quote there. We demonstrate how to construct pure functional programs that precisely specify the behavior of effects. And fast forward just a few years to 2008, or 1 year, 1 year to 2008, and in this famous paper, Data Types a la carte, which introduces a ton of really cool ideas, we see a representation of free that we can identify. It looks exactly like the modern day incarnation, at least in languages like Haskell. And what he points out in his paper is an additional advantage of this two-step approach is that the terms we write are pure Haskell values, information we can exploit if we are interested in debugging or reasoning about effectful functions. And that's something that you're going to see in free, is this idea that maybe we don't have to embed chunks of machine code in our programs. An I/O of anything is a chunk of machine code that's embedded in a program. And the idea with free is maybe we don't have to do that. Maybe we can just describe the semantics of the effect as a data structure and embed that in our program and save actual machine code until the end of the world. Nothing? Okay. And then 2008, we'll just skip over that. 2008, they made a big performance breakthrough in free monads. 2015, fast forward all the way, a ton more papers, and you have sort of what I would consider state-of-the-art free monads in 2015 by Oleg, called Freer Monads, More Extensible Effects. And that's super slick. Your free monad or your higher kind of type that you're using to describe the set of operations supported by your program, the set of effects, no longer has to be a functor, and it's really, really fast. And also you can eliminate boilerplate by using more advanced features of Haskell's type system. So really cool stuff. But look at that, 2007 to 2015. There's a point I want to hammer home tonight or today. It's that free monads are in their infancy. They've just gotten started. So if you can imagine what's going to happen over the course of the next 10 years as people invest more and more into researching not just free, but other approaches that are inspired by free, I think that's going to be way more interesting than all the stuff we've discovered to this point, is the stuff that's going to happen over the next 10 years. Okay, so I have widely critiqued functional programming as being in some sense too big. In other words, you can write functional programs that are disastrous and impossible to reason about and look exactly like imperative programs written in C. And Conal Elliott wrote this blog post that some of you have probably seen, and it was titled something like C is a purely functional programming language. And it is, right? If through the right lens, you can view C as a purely functional programming language. That doesn't mean you can reason about C code. Well, this is an example of something that I see in programming in the large, functional programming in the large, is code that is purely imperative, and honestly, it's hard to reason about. It tangles lots of concerns together at lots of different layers inside your application. And I hate code like this. I hate it whether it's written in C or I hate it whether it's written in Haskell. It makes very little difference because it's hard for me to understand and to keep those concerns separate and to understand their interplay. And nonetheless, this is, if not actual code, at least based on actual code, you'll find tons of code like this out there in the wild. And, whoa, what's that? Oh, that works. So a while ago, sometime last year, I think, I came out with a blog post that turned out to be controversial. I know, I can't even believe it. Me write a blog post that's controversial. The good old days. Well, this blog post, basically I came to the conclusion that the way I want to write my functional programs is basically as layers of an onion. And I want them to speak at different levels of abstraction. I want one level to, let's see here, this doesn't look exactly right. Let's change the theme. That's better. It's not terrible. I want the core of my application to talk in the business domain, And then sort of other parts further out, closer to the bare metal, to talk in the API or operating system domain. And then at the end of the world, I want things to talk in like the service domain, or I can even imagine going further and boiling things down to processor instructions or JVM bytecodes. Yes, go.
Isn't this just rehashing like sort of the quote DSL revolution of like, you know, the 2006, 2007 era? I mean, Ola Bini wrote a blog post about this in 2006 that was basically like invent your own little languages here and there. So what are you bringing to the table that he didn't?
Good question. I'm bringing the free monad and I'm bringing type safety. And so these DSLs can be implemented in the host language with almost no boilerplate. And that's the big problem with almost no boilerplate. In Haskell, literally no boilerplate. In my like punier version of Haskell, pure script, there's going to be some boilerplate. But yeah, it brings the ability to do this, which like people have long recognized the value of DSLs, but they take time and they're not type safe, and you have to invent parsers and all this other crap. But in my opinion, free has taken all that away, and it allows us to speak in the business domain and then express how that domain maps to other domains. And I only recently sort of saw the connection between this style of programming, in which our entire program is basically a series of multi-staged, possibly optimizing compilers, down to the bare metal, or as close as you want to go to that, and denotational semantics, in which the meaning of a term is given by defining it in a compositional way that maps it into a target language, a host language. And that to me was amazing. And when I saw that connection, I'm like, this is the future of programming. Not free monad necessarily, but this way of thinking about programs as layers of an onion in which we express the semantics of this part in terms of something that's lower level, that is the future of programming. So, this is how you do it. You just define your different operations, operational functors, which have all the lists of different operations, and then you can define something like an interpreter, which takes a single operation, an f of a, and translates it to a program in free g of a. And this is just one way of defining an interpreter, but it's one that is extremely compositional, because every interpreter deals with a single operation at a time and expands it into a program in a different in a different functor, G. So it takes a program described in F and translates it to a sequential or it takes an operation described by F and translates that into a sequential program described by G. And when you do that, you can build up these really wonderful trees. Like you can actually model things like, okay, my application is talking up here, and I'm going to log at the level of my application, but I'm also going to send some HTTP requests, and then I'm going to compile that down to socket, to a socket-based algebra, and I'm going to also log at the level of the HTTP so I can get requests and response and stuff like that. And the composition of your final interpreter is a total tree. It's actually not linear. And then you can end up sort of chaining all the different, composing all the different terminal, the leaves of this tree together, collapsing them all together to produce a program in the composition of all your different operational algebras. In this case, it's G and J and K. And that's cool, because at the time I thought, hey, that's a tree, and monad transformers are a stack. So monad transformers can't do that, right? And I thought, well, this is an argument for using free. Turns out I was wrong. Some guy out there, Oliver Charles is his name. Like 2 days later, he had this little piece of code which he posted on GitHub, which demonstrates you can actually do the exact same thing in MTL. And how do you do that? It's a sort of weird linearization of the tree, whereby an interpreter, which in MTL is given by an instance of a type class, an interpreter, actually ends up having to do the work, in this case of logging, and then it delegates to the next one in the chain. So that's a bit of boilerplate, and I want to call your attention to it. Whenever you take a tree like this and you smash it up and linearize it, then you're going to have every interpreter paying attention to things that it shouldn't. It's going to have to delegate to a different one in the stack. And that's boilerplate. Why does that have to be the case?
Well, you have to linearize your example just from the previous slide too, unless you literally want a logger for sockets and a logger for HTTP, and you want them to be two separate algebra. Like, really, you want to have one logger algebra. And so you're linearizing, you're just doing it through coproduct rather than doing it through type classes.
And the key thing there is that, yes, the key thing, however, is that every interpreter does not need to know or pay attention to the operation of any other interpreter. For example, a logging interpreter can literally produce nothing. It can produce a unit. Whereas with MTL, it's going to have to produce that A value, and it's going to have to produce that by delegating it to it. So it's a little bit of a conflation of concerns there, in my opinion. But it's not catastrophic, right? You can do it. It's not catastrophic, but you are conflating the concerns of different interpreters. And you're making it so you're going to have to produce a value in every single interpreter through the process of delegation. So it makes what is much more implicit and specified at a different level, it makes it explicit and forces you to tangle concerns together of different interpreters, which is not a fatal flaw, by the way, just an inconvenience. So round 3, first round went to free, I thought, and then round 2, MTL strikes back, and we're back at square one with MTL having its own set of benefits, not the least of which are much higher performance than free, and having all these wonderful libraries of monad transformers out there that you can just plop into your application and compose together. However, round 3 is going to go to free for the following 2 reasons. I'm going to give you 2 reasons today that I think are extremely compelling reasons why we should pay attention to free. And the first one is analysis. So keep in mind that when you're using free, you're building data structures. You're not running hunks of machine code. And one of the ways that you can model a program is as a sequential, basically a sequential program of parallel program fragments in some DSLF. And what this gives you the ability to do is to, free app here is not a free monad, it is a free applicative. And free applicatives have the rather fascinating property that you can explore them and discover their structure without computing runtime values. So you can do things like analysis and optimization. And that's amazing because what it does, there turns out to be like huge snippets of software that can be written in that fashion as like totally parallel operations. What it gives you the ability to do, among other things, not just make higher performance code in theory because you can explore sections of your program and optimize them into a different form that's higher performance, but what it gives you the ability to do is to make your set of operations, your set of F operations, smaller. In MTL, you have to list every single operation supported by that DSL. So for example, if you're modeling a file system, you're going to have rename file and move file and copy file and delete file and append to file and this and that. And so pretty soon you're going to have probably 20, maybe 40 different operations representing a file system. Why? Because for performance reasons, you have to do that. Even though you can define a file system probably in terms of 4 operations. For example, the operation of move could be described by duplicating a file and then deleting the original one. But would you ever want to do that if you were moving a file? Like actually duplicate the file and then delete the original one? No, you'd never want to do that. But in MTL, you're basically going to be forced to list all of them because you want to be able to special case the operation of moving and capture the sort of semantics that, okay, this is a move without the ability to sort of statically explore what that little parallel subprogram might be and discover, hey, we know that there's going to be a duplicate followed by a delete, therefore we can optimize that semantically optimize it into a move. Yes?
But, I mean, if you're working in applicative, you can't even express the fact that this effect is followed by this effect.
Yes, you can. It can be baked into the laws of applicative. And in fact, like if you have a monadic instance for your applicative, it's by definition sequential, and if you don't, then you can define it to be sequential or not. So what you do is, and in applicative-only parsers, the applicative semantic is assumed. So it's parse this, then it's parse this, then it's parse that. Heckle defeated. Yeah! Okay, so what does that give you the ability to do? Well, if our file system went down from 20 operations to just 5, we can reason about that easier, a lot easier. And like we can implement something that's correct much more easily. And then we can show how these 5 operations translate into, for example, operating system calls or something that's lower level. We can provide a denotational semantics for our file system language. And that's really impressive. And in MTL, you're going to have in all 20 operations. And if you want to log that, that's 20 logs, 20 proxies. It's going to be messy, complicated, and what it does in practice is make the classes in MTL very, very large and cumbersome and more difficult to reason about, because you have to think of all the, not just what the program means, but also what are the performance implications of these things. And when you have a free app program in F, you can just peek ahead and discover all these things and then convert those into operations that are semantically equivalent but can run many, many, many times faster. So the other benefit of free monads that I want to talk about. Fortunately, I beat Daniel to this because apparently he's already done it in a secret repository, something I only learned today, is mocking. What? No heckling?
I was just going to say, I think Daniel's been very public with his mocking.
I mean, like, mock testing.
Oh.
No booze? Come on.
Fun of testing?
You call yourself functional programmers and you don't boo mocking?
I just smoke it.
Yeah. Yes, we functional programmers, we mock mocking, right? Because mocking is something you have to do generally when your functions take units and return unit. And you have to mock out that static class, or mock out this, or mock out that, or mock that indecipherable library over there. But nonetheless, I actually think there is an extremely compelling case for functional mocking.
Using Spring.
Damn you. And what is that? It is integration and system testing. I hate interacting with systems. I hate it. I hate it whenever my application calls out to the operating system or a socket or some cloud API or the browser or whatever. It's terrible. Why? Because those systems have their own set of unreliabilities, even third-party library. I don't want my code to fail based on whether or not there's a hiccup in the operating system or a hiccup in a cloud service API or even like a tiny patch version of some library out there that introduced a bug that they're quickly going to discover and fix. I want my programs to be totally specified from the core to the outside. Yeah?
So, I don't know exactly what you mean by mocking, but I'm assuming you mean you're switching out interpreters for your free ASP. So instead of, when you're combining all these DSLs that you wrote free-wise in your co-products and then interpreting it, you're kind of delaying some of this functionality into the interpreter. And then so when you switch out a mock interpreter, are you really only testing half your program? Or we're going to say even less than half your program? Because rather than like having your functionality of how, for instance, like state your option works, you might have to bake that into your free interpreter to carry some of that around.
Right, John DeGoes doesn't believe in test coverage.
No, I do, but here's how I view it. View it through the lens of denotational semantics, and our job is to take a term in some source language and translate it into a higher level target. And so what we have to do is we have to verify that's correct, or we have to, at least have sort of a rigorous semantics of what that means, and ideally test for that case to verify, okay, this one should be translated into this. And we do that at every layer of the onion, and then we get to the outside world. And at the outside world, well, instead of like actually running the thing in the external environment, which is slow and prone to failure, prone to hiccups, indeterminism, all that crap. What we do is we externally verify that the outer ledge of our application, our lowest level target language, if you will, we verify that is correctly translated to operating system calls, but not in our application. So for example, we might have if we translated this stuff all the way to bytecode, which would probably be overkill, probably. I'd like to do that though, I really would. If we translated it all the way to bytecode, then all we would have to do is verify that the JVM machine would execute that bytecode in accordance with the semantics that we've given it. And in so doing, like the same way for like a REST API or like a socket, if we translate REST API calls into HTTP languages and translate that into socket languages, then all we have to verify is that socket language has the correct mapping, and that is going to be an integration test. It's going to be a system test. It's going to be nasty. It's going to be messy. It's going to be failing sometimes for reasons that are unrelated. But we can take that, we can stick it in its own library, and we can run it very thoroughly, very infrequently. And then our language, it never has to test those things. It can just assume that the final language that it's speaking to, or final set of languages, are faithfully implemented and tested in the individual libraries that surface them. So, purely functional mocking, that's a repository just recently created to demonstrate this technique in advance of Daniel. How are we going to do this? How are we going to do purely functional mocking? Well, every single operation in a free algebra can be expressed using a data structure. And the meaning, the interpretation of those type parameters, or data op, is an operation. Think of it as some f of a, or rather f of c. The meaning of that is as follows. A is what you provide the operation. So if you're opening a file, what do you provide it? Yeah, the path. So A is a string in that case, and maybe it's not just a string, maybe it's a tuple of the string, the path, and the read mode or the open mode, whatever. And then B is what you get back from the operation. So for example, if you open a file, if you have an open file operation, you're probably going to get something like a file handle back. So B would be a file handle. And then C, you can think of it as the whole that would ordinarily represent a continuation of your program over time in the free encoding. So once you define this, you can actually define a polymorphic prism, which allows you to say, for all C, I can give you a prism that maps between an f of C and an operation in A, B, and C. And that prism allows you, functionally what it allows you to do is to say, okay, my operation, you have to provide it an A, and it's going to return a B. And I can take and I can translate between an f of C and an operation in A and B. In other words, it's a way of, in general, we're going to have a great many set of operations, and we're going to want to be able to pick out a particular operation. So how do you select for a term in a sum in functional programming languages? Use a prism. And this prism has to be a polymorphic prism because the C doesn't matter. You don't care about the C. The C is the continuation of the program. You don't really care what it is. You just need to keep the types, the same and aligned. So that's why it's a polymorphic prism. But it allows you to take an operation and possibly pull out that op of AB from some f of C. So once you've defined this notion of a prism, it is really, really powerful because a prism cannot just possibly extract out a term from a sum, but given that extraction, it can turn around and it can create the sum value that has that type of the sum. So what that means is I can define three functions which, given a prism, will create a read-only operation, a generic operation that has read and write components, and by by read, by the way, I mean that the operation only returns something. So for example, if I have an operation like a console getLine that's just going to return something, I don't give console getLine anything. And a write operation, which is only going to put something, it's not going to return anything except for unit. And for example, a put stir line or a write line operation is going to be a write-only operation, or an op, which is like a little bit of both. From here, I define a mocking operation, and this is skolemized. So there's actually existentials hiding in here, which you can see in the nested for alls. But what it basically says is, okay, I'm going to store, there exists an A and B such that I have an op prism for FAB and an assertion of A that's going to check to make sure the input's good and produce some error message, and also a function that can take what was sent to that function and turn it into a B, which is the return value for the operation. Does that make sense? And then I have a mock spec, which is basically a list of these mock ops. So very, very simple representation here. So I have a list of all these different mock ops. And then I can define this, what you saw on the previous slide, the type assertion, which is just a mapping from A to either a string or unit, and a few little helpers like assert equals to verify two things are equal or produce an error message. And then I can create these expectation functions, expect read, and expect write. Expect is the fully general purpose expectation. And in that version, you can specify an assertion for your input. You can specify a way to convert your input to your output, and that's going to yield one of these mock specs. And mock spec, again, is just a state monad with a list of these mock-ops. So this combines in the usual way. And then finally, I can implement this function, which is actually not that complex. You can look at the implementation on GitHub. It's reasonably simple. And it just says for any mock spec f, if you give it a program in f, it's going to either return a string or whatever that program computes by running it against the mock spec. And here's an example DSL to show you how this thing works. It's a console F, sort of a classic example here that has the following operations, a write line operation and a read line, which do exactly what you think. And then I define the polymorphic prisms that allow you to extract out those operations from a console F, maybe extract them out, or to, once you have something that's extracted, push it back into a console F. And here are little helpers that allow you to read and write little programs in console F, free programs in console F. And finally, I can give you an example specification. So this is my example specification. I'm going to expect a write line, and I'm going to verify that it equals what is your name. And then I'm going to expect a read line, and I'm going to provide world. And then finally, I'm going to expect a write line that verifies the result is equal to hello world. So what is this? This is an interactive program that's going to write a line of input saying what is your name. I'm going to type my name in, and it's going to spit out hello world. Yes?
I think I missed it, but what does it do when it doesn't get an expectation?
So I will, yes, it will give you an error message, a very descriptive one. And I'll show you that. So this is a good program. You run it using this, and it's going to say success, because this program does what it should. Here's a bad program that gets a little too friendly. What is your first name? And what does it tell us? Well, it says failure expected what is your name, but found what is your first name. This is another bad program. This program doesn't really care what your name is. So you get a failure saying unexpected operation. And you could pretty that up, by the way. You could include the operation name or other types of things, or even a custom error message. And this is a dismissive program. It isn't very inviting at all. It just says, what is your name, reads it, and says goodbye. And you get a very descriptive error message. You see it gets past the first one, it gets past the second one, and then finally it gets to the third one. It's like expected hello world, but found goodbye world. And then finally, this is an empty program. Satisfies the same type as the other, but it doesn't do anything. And this says unexpected early termination, 3 operations remaining. So look at that. Go ahead.
So you said your mock spec was the state monad. where is the state?
So, run mock. Well, so these are the programs, and I didn't show you me running the program, but basically there's this function here for running it. Where is it?
Run mock.
Where is it? Yes. Earlier? Yeah, there.
Yeah.
So you specify the mock spec, which I already created with the do, and then you specify that thing.
Yeah, but the type of mock spec includes state, doesn't it?
Yes. So you have to run the state after you run the mock.
Yeah,
right?
I'm just wondering where the state is and how.
The state only consists of the list of mock-ops.
Oh,
So
I see what you're doing.
It appends a mock-op every time. Every time you have one of these expectations, it appends a mock-op into that state. And so it starts off with the full state and then ends up just peeling one off every time. Super simple. Limitations addressed. Wouldn't it
be great, John, if you could compute later assertions from the previous ones, huh?
Yes.
Wouldn't that be nice?
That is left as an exercise for. Let's see whose one is open source and on GitHub and already presented at LambdaConf before yours, shall we? Exercise left for reader. So the judges pick a winner, and it is MTL. Wow, that was unexpected, right? So MTL is enterprise grade.
It's web scale.
It's web scale. Yeah, I like that. It's web scale. I mean, it is. It's like, Spring or enterprise Java Beans, or it's the solution you go to solve problems. Yes.
So when you were talking a couple of rounds ago about free app and being able to sort of inspect on structure and computation without actually running, do you have any opinion on that versus like what is now out of fashion in the Haskell community, which is arrows, which provide a lot of the same niceties of applicatives, but with an odd syntax. But have you looked at that as an alternative to free applicatives?
Yeah, I really like free arrows. I really do like them. I wish I could have made the talk previous to this, but they're super powerful, super interesting. Or even like free profunctors, which maybe have a little less structure.
There's first-class syntactic support within Haskell.
Free arrows?
For arrows in general.
Oh yes, arrows, yeah. The arrow notation, super nice. I envy Haskell's features sometimes, programming as I do in pure scripting. So MTL, it's the enterprise grade solution. It has the highest performance. It has reasonably good performance. It's well understood. This is very thoroughly explored. And I don't feel at this point that free is in the same position. However, I do think free is a really good runner-up. And even though it's not the enterprise Java Beans of composable modular effects like MTL is, it is very, very interesting. And it's the early days for free. I think the thing that we'll get out of free is basically type-safe reification of your computational model, whether that's sequential or parallel or arrowwise or whatever it is, the total reification of that, and the description of your program as a declarative data structure, which I like for lots of reasons. One, because I'm always arguing for programming languages that can't actually do anything in the real world. They just produce data and stuff. But also, I think it points towards a future in which we define our programs only using denotational semantics. And possibly points the way towards something that's after functional programming. Something algebraic programming, if you will. That I don't know exactly what it looks like, but it certainly would have as its core, it would allow you to use denotational semantics to express layers of translation between your different layers of your program, but without any performance overhead and without any boilerplate. It would be designed for doing that type of a thing. And so for that reason, I picked free as a runner-up because I think it's something we need to pay attention to and invest in more, even though I wouldn't necessarily recommend you always use free instead of MTL. So that's all I have.